To remind you some notation that's recurring in all 4 lectures. Delta is my short distance cutoff, and D is the space-time dimension. So we live in 4 space-time dimensions, 3 space and 1 time. In the last 2 lectures, I'm talking about things that are more recent developments on HepTH related to this title. And last day I talked about entanglement and RG flows. I just wanted to add one comment, which was that at the end of the day I had a list of questions, and the last question was, put your favorite question here. And John made a suggestion, which I think I was too quick to dismiss. After a glass of wine and sitting down again last evening, I thought, just to remind you, his suggestion was, well, could we think about RG flows and perhaps C theorems in the case where we don't have Lorentz invariance? And what I said is, well, we know that there are counterexamples. When we lose Lorentz invariance, then, for example, the entire proof of the C theorem that I gave you yesterday, well, is out the window because that was an essential ingredient. However, in retrospect or after a glass of wine, I thought that, it's still interesting to ask, what are the boundaries where the C theorem applies? And so we know there are some examples where the C theorem would be violated, but, are there other cases where we don't have Lorentz invariance, but it is satisfied? Could we remove Lorentz invariance and replace it with some other properties that the field theory has to satisfy? Or could we amend the definition of the C function in some interesting way? So I think John's question, there is something interesting there, and it's sort of to explore, what's between what we know with the Lorentz invariant theories and the counterexamples where we know that the C theorem is not applied. So today's lecture, though, what I'm going to do is look at the holographic universe according to his article, and the way you do that then in this lecture is you just write holographic in front of entanglement entropy. And so depending on where you come from, you may have had seminars on lots of, that had this flavor where they write holographic and then something here. The something here might have been QCD, it might have been hydrodynamics, it might have been superconductor. But basically the theme there in all of those is that it's a mashup between 2 different topics. You take some topic in a respectable field of physics, condensed matter, quantum field theory, and then you try and understand that from the perspective of something known as the ADS-CFT correspondence. And so this, or another name for it is, of ADS-CFT. And so this is an idea that's emerged in string theory about 16 years ago now, I guess. And, well, given my audience, what remains, I feel obligated to try and tell you a little bit about what the ADS-CFT correspondence is all about. And again, I have to make the same apology I made yesterday for the experts in the field. I apologize for butchering this beautiful topic with a 10-minute introduction. And for the non-experts, I apologize for butchering this beautiful topic with a 10-minute introduction. So the basic idea, though, is given on the board here. The ADS-CFT correspondence postulates the equivalence of 2 kinds of physics. Or rather, another perspective is that it's a dictionary that says there's one set of physical phenomena, but there are 2 languages or 2 mathematical frameworks with which I can access or describe that same physics. And so one side of the correspondence, or one side of the equivalence, comes with the letters ADS, and so that corresponds to anti-de Sitter space. And so on that side of the equivalence, what we're supposed to be studying is quantum gravity. It's quantum gravity in the presence of a negative cosmological constant. On the other side of the correspondence, what we have is CFT, and that's something we ran into already, so that's a conformal field theory. So on this side, I'm just doing quantum field theory, and in particular on this side of the equivalence, there's no gravity in sight. But to make the equivalence even more preposterous, on this side, I'm studying my CFT in d space-time dimensions, my convention over there. But on the other hand, in the anti-de Sitter space, where I'm studying the quantum gravity, we're actually studying it in d+1 space-time dimensions. So there's an extra dimension on this side of the equivalence. And that's why the word holographic comes into the picture. This is a realization of an idea in quantum gravity called holography. It actually emerges from studying black holes, thinking about the information paradox, storing information on horizons. But I'm not going to go into any of the details there. What I did want to say is, well, one, it's still a conjecture, but it's something that in the past 16 years has withstood the scrutiny of literally thousands of different investigations. And the other thing I wanted to say is that it's not something that someone just made up, at a Saturday afternoon barbecue, but it's something that came from somewhere. And actually, nope, we have to do something first. To give you an idea of where it comes from, I have to step back and I have to tell you some basics about what string theory is, or some essential ingredients. So we're going to step back for a moment. And any string theory, there are two essential ingredients. I mean, the basic idea is when we try and describe fundamental physics with a quantum field theory, implicitly the idea is that the fundamental excitations, in some sense, had their existence as particles. And so in string theory, we're replacing that with the idea that they're now extended in one dimension, hence the name string. But those strings all have a tension, or an energy per unit length, which gives rise to a scale in the theory. So in our favorite units where h bar equals c equals 1, I can write the tension as 1 over the string length squared, and you can think of this as the typical size of a string. And so we should think, well, we don't see strings around us, so if strings are describing the real world, that's a tiny, tiny scale. The other ingredient is that there is a dimensionless coupling, which gets the name G substring. And so what that's telling us is about the probability for strings to interact. And so we can all do string theory with our hands here rather than draw a picture. The idea is that I have two strings, they come along and touch, and there's a probability that the strings will actually join and form a larger loop. Or the reverse could happen. If I have a large loop, it could, through some fluctuation, touch itself at some point and break apart. But there's this is a quantum theory, and there's some kind of probability that happen. Most of the time, at weak coupling, most of the time the strings just pass right through each other. But there is a probability governed by this coupling that they will do this joining or falling apart. So those are two ingredients that you'll find in any relativistic string theory. The other comment was that string theory, well, I won't write it down, but what we discovered in the 1990s was that string theory is more than just a theory of strings. And so how did we discover that? Well, the strings come in two kinds. There are closed loops, or so-called closed strings. But then there are also strings that are open intervals. And what kind of strings appear, if I have open strings, I'll always have closed strings, but the details depend on the kind of string theory that I'm building. But these are then the open strings. the open strings have ends, and so what was realized is that those ends are supported on certain subspaces. Well, okay, here's so much for my three-dimensional drawing. I can have a subspace, so I could have a string that starts and ends on the same space, or it could start on one and it could end on another, like that. In contrast, the closed strings aren't confined. They can wander through the entire space-time or move anywhere that they want. Well, okay. But these subspaces, after a while, or what was realized is that these are actually dynamical objects. They're new ingredients. They're other kinds of extended objects that appear in certain kinds of string theories. And they were found to play an important role in all sorts of interesting physics, especially when we think about the case not where G string is small and the probability is weak that the strings interact, but when G string becomes large. Okay, so given these ingredients, what can I do? Well, what Juan Maldacena did in 1997 was he thought about a certain order of limits. So we're going to start up here in the top left-hand corner. We're going to think about a set of, I forgot to say. Okay, these subspaces are called D-branes in the nomenclature of Joe Polchinski. The D stands for Dirichlet, and that has to do with some technicalities about boundary conditions for these open strings being tied there. So now we've got a new name. A D3 brane is one of these subspaces with 3 spatial dimensions and 1 time. And so up in this corner, we're going to start thinking about a situation where we have n of these D3 branes all piled together. And so as I've described it here, it's a theory of closed strings which wander around and open strings that are tied together or tied to these n D3 branes. And so there's one interesting limit that one might take, which is a low energy limit. In particular, if we think about energies that are much less than the energy scale defined by this string scale, then basically we're throwing away all of the stringy excitations, and we just have the lowest energy, or well, I want to say the ground states of the string, but I have the simplest excitations in the string theory. And it turns out that in that case, what happens is it reduces down to a quantum field theory. And in particular, the open strings here turn into a certain kind of gauge theory with a gauge group known as UN. And so this is a theory very much like QCD, or the theory of the strong force, with an exotic group perhaps here. And there's also exotic matter. I haven't told you this, but this is a supersymmetric theory. So there's strange kinds of particles or quarks running around in that version of the gauge theory. Another limit, another thing that we can play with is the coupling constant. And so another limit that we can do is we can take that theory and we can think about strong coupling. If I have this gauge theory at weak coupling, I end up with the gauge theory at strong coupling down in the corner here. Now let's think about taking, or what Juan instructed us to do is think about taking the limit in the opposite order. So we start here, and the first thing we do is we take the strong coupling limit. What happens then is that we had these D3 branes, and they were, they were dynamical objects. They coupled to these closed strings, but in particular they coupled to gravity. And so they develop a big gravitational footprint in the space-time. And at the end of the day, what is a good approximation to this theory at strong coupling is just a curved space-time which solves the gravity equations for these ND3 branes. But in particular, down in this corner, I only have the closed strings. In some sense, what I'm doing here in giving this description is I'm integrating out these strongly coupled open strings, and the net effect of that is to replace it with a new effective theory, which is just this curved space-time theory. Again, what we do then is we take the low energy limit. In this case, I think Daniel described to us how in a gravitational, around a black hole in the gravitational potential, I can have interesting excitations well, deep down in the potential, which are still low energy with respect to infinity. And so in this limit, what we end up with is closed strings, but they're only the closed strings that are propagating around deep in the throat, or in this strange geometry very close to the D3 brains. And so we took the limit in two different orders. We ended up with two theories which look very different. A strongly coupled gauge theory and closed strings propagating around in some strange curved space-time. And so then the audacious claim that Juan made in 1997 was that even though these look very different, we're still describing the same physics here with those two different theories. And so that then gives us our favorite example, or the string theorist's favorite example, of ADS-CFT, where on the ADS side, what we have is type 2B string theory. So this is just going to be a bunch of buzzwords in case you hear them. Well, type 2B, well, okay, we'll call them superstrings on a strange geometry, which has the name ADS5. It's a 5-dimensional ADS space. There's actually another piece of the geometry floating around, which is a 5-dimensional sphere. And there's a certain background field that knows about the N of the ND3 brains. And that's what's supporting this interesting geometry. On the other side, the gauge theory is a 4-dimensional theory. Yeah, as I said, there's some kind of extra fields, or there's extra symmetries, and so it has, it's a supersymmetric Yang-Mills theory. And the gauge group, as I said, up there is UN.
So are the strings quantum mechanical objects, or do they have fixed position and dimension?
No, they would be quantum. They're quantum mechanical objects.
But they can also be created and
Yep. Yep. So in fact, when I think about Hawking radiation in this theory, the things that are being created are actually strings. The photons, or the zero mass things that Daniel talked about, would be the lowest excitations of those strings, roughly speaking. The other excited strings would have very big masses that was governed by this scale L string, and so it would be a very low probability in the typical process that we would excite or we would emit a string like that.
So two-dimensional closed objects? I mean, why do they have to be one-dimensional?
That's a long story that I would never get to the end of the lecture if I went there, but you can try and ask me later. So this was just a favorite example. Wow, okay. No. So, well, I'm not sure what you mean. I mean, well, you know that this is a 10-dimensional theory, which I didn't say. This gauge theory, though, is confined to these D3 brains, and so they only know.
From your general standpoint, you had a D plus 1 to D dimensions.
Right, so I had a 4-dimensional gauge theory. The general framework. Yeah.
D plus 1 to D, and so you would want this over here.
Right, so
You want to see the holography on the right-hand blackboard?
What is, right?
well, I want to point at that 5. That's the holography. Here's my anti-de Sitter space. The 5, well, whatever. The 5 means it's a 5-dimensional anti-de Sitter space. And so I've got 5 dimensions here and 4 dimensions here.
I guess he's asking why the strongly coupled gauge theory on the right-hand diagram is a dimension lower than these low-energy strings in the D3 geometry.
Yeah, but so something I don't want to tell you, but Paul already knows, is that this is actually a 10-dimensional theory. In going to this limit over here, I mean, I also didn't tell you that I threw away the closed strings because they decoupled from the open strings. But these guys, or these strings, or this field theory only knows about 4 of the dimensions. And so it's really in that step that the number of dimensions went down. It turns out, by following all the details here, that I'm still in a 10-dimensional space, but the anti-de Sitter part of it is 5-dimensional, and then there's this closed, the extra dimensions here. But I guess it was really here that I restricted this theory to a lower dimensional subspace. The caveat that I wanted to say is that this sounds very bold, that we're studying quantum gravity over here in anti-de Sitter space. And one of the secrets is that we don't really know how to study quantum gravity in anti-de Sitter space. And so most of the time, what we're actually going to study here is classical gravity. In a space with small curvatures. So that means that we're actually studying it in a limit where all we're doing is we're studying Einstein gravity in anti-de Sitter space. Einstein gravity coupled to lots of interesting things. But as I said, this is a limit, and so there are actually 2 things that we're adjusting. One is we can think on this side that we're taking a large central charge. Or in this language over here, that means that we're taking a limit where that n, the rank of the gauge group, or this flux here, was becoming very, very large. The other thing that we're doing is we're going to strong coupling, by which I mean the effective coupling is strong. And so, again, in this language, that's the Tuft parameter, which is a combination of the natural, or the fundamental Yang-Mills coupling and n, and that's, again, becoming large. But to make progress with the entanglement entropy calculations, we have to take a closer look at anti-de Sitter space. And so I will look for the eraser. And I will write down okay, so we're gonna look here at anti-de Sitter space. The words are that this is in some sense I said we're studying Einstein gravity or Einstein's equations, and so this is the simplest solution of Einstein's equations coupled to a negative cosmological constant. Alternatively, we can say it's a maximally symmetric geometry with negative curvature. I'm going to write down a metric here. So in this metric, one of the things that we see is that there's this parameter L, capital L, and so that is the curvature scale. Or it tells us how non-flat the geometry is. This part of the metric, here I've got time, and I've got some spatial directions. These are the CFT directions. And on the other hand, well, I've got an extra coordinate here, so this is the extra coordinate, the extra holographic coordinate. So what does that space-time look like? Well, here's a cartoon of our ADS space-time. And so, well, okay, just here I've got R. It runs up the board. The T and the X's are sort of in these horizontal directions. in my cartoon, what's up here or at the top is r equals infinity. So it is a cartoon. It's not a Penrose diagram. That's the boundary of the anti-de Sitter space. And in some sense, we can think that the CFT lives in that space or lives up there. Down here, we have our d plus one dimensional space-time, and the technical lingo is that's the bulk, and that's where the gravity lives. Now, why did I make the cartoon with this fluted shape? Well, if I pick a coordinate distance, say a delta x here, and I draw a delta x on that slice at very large r, the proper distance in my geometry isn't just delta x, but I'm going to have to multiply by a factor of r over L. And so when r is very large, the proper distance associated with a given delta x is large. When I go down into the bulk where r is becoming smaller, the same delta x gives me a smaller proper distance. And then, even at smaller r, the delta x is even smaller. And so that's what this sort of flute or funnel shape is supposed to represent. That the horizontal distances as I move down in r, if I fix the coordinate separation between 2 points, their proper distance, or the real distance as measured by this metric, is getting smaller and smaller as I move down. And so a comment about ADS-CFT is that I said that there was a dictionary, and so one of the interesting entries in that dictionary, which I'll make reference to, is that if I have a black hole in the ADS space, then on the CFT side, I can think of that as a thermal state. Since I'm talking thermal here, there must be a temperature, but Daniel told us that black holes have a temperature, the Hawking temperature, and so it's very natural then that the Hawking temperature just becomes the temperature on the other side. And there's a formula that I'm just going to write down because I want to make a comment. In these coordinates, well, I didn't tell you what the black hole is, but the Hawking temperature is given by something like the position of the horizon over pi times the curvature squared. And what I said was that's the CFT temperature. So now down here in the bulk somewhere, the space... there's going to be some kind of a horizon, a black hole horizon, at r equals RH. The thermal bath is also going to have an entropy, but we talked about, or Daniel talked about, how that given a horizon, there's going to be an entropy, the Bekenstein-Hawking entropy associated with that. And it's natural then that that becomes the entropy of the thermal fields. Sorry? Yep. This would go down all the way to r equals 0. You should ask me again when I, provoked by Daniel this morning, I'm going to draw a Penrose diagram, and you should ask me where that is in the Penrose diagram. Okay, so here there's just an entropy, the Bekenstein-Hawking entropy, which is the area over 4G. It turns out using this formula that turns into something like the volume of the space times the CFT temperature to the d minus 1. And you can almost see that in that I'm going to be integrating over the x's, say, at this position, and there's going to be some redshift factors that are associated with that. And so there's an r over L associated with each one of those, and so that gives me something like a temperature to that particular power.
What you did in the last lecture,
Yeah.
Essentially, a lot of different types of conformal field theory.
These are very special conformal field theories that have a...
Why do you have temperature in conformal field theory?
Oh, okay. So I'm not talking about the vacuum again. This is just a special case. What I'm talking about is rather than empty anti-de Sitter space, what I'm doing is I'm changing the geometry, and I'm not telling you what the metric is, but I'm saying that down here in the bulk there's a black hole now. And the claim is that that black hole is related to some kind of thermal state in the CFT. And so the temperature, where did it come from? Well, it came from the fact that black holes have an associated temperature, which then gets mapped to a temperature in the boundary theory.
So that geometry at infinity corresponding that geometry.
Sorry? What? I didn't...
Geometry for black hole.
Yes.
When R goes infinity, that gives ADS space.
No. This whole thing is the ADS space. When I add that to the picture, this is actually an ADS black hole. We can think, though, that there are tails. The geometry is modified, and so by studying the tails of how the metric is approaching this particular form out here at infinity, I can realize that there's a black hole down here, and I can realize then that there's a temperature, there's an entropy, there's an energy density associated with that.
You're supposed to point out that the ADS geometry will have a periodicity in the imaginary time when you analytically continue. That's where the temperature comes from.
Okay. Does that make you happy? Okay. I don't know. I think Daniel already told us that, didn't he? It makes Daniel happy. Okay. Oh, yeah, one of the actual reason that I wrote, well, okay, I wrote that down for several reasons. But here you get a hint as to why holography wants an extra dimension, or what the holography is doing with an extra dimension. You can see that there's a temperature, but as a HepTH person, you can associate that temperature with an energy. And so you see that energy scales here are being associated with scales in the radial direction. And so that's well, part of the holographic or the ADS CFT lore, that energy is roughly related to radius. And so what are we doing when we probe, or when we probe the geometry down here at small radius? What we're doing is we're probing degrees of freedom in the boundary theory, or in the boundary CFT, that are long wavelength or low energy degrees of freedom. Alternatively, when we probe the geometry way up here at large radius, what are we doing? We're probing degrees of freedom in the boundary CFT that are high energy or short scale, short distance degrees of freedom. And then the last comment, provoked by Daniel, I have to draw a Penrose diagram. Well, which he actually already did, except, well, I'm going to draw, because we're the high-tech lecture, we're going to draw a three-dimensional, look at that. So if we do the Weyl rescaling that compactifies anti-de Sitter space, what you end up with is something that I'll represent here as a cylinder. So there's some radial direction. The boundary I can think of as an SD minus 1, and then there's time. Maybe I should say Penrose diagram. Yep, okay. But in particular, as Daniel was saying, is there's this time-like boundary here, and so we have to make up, well, there has to be a rule as to what the fields do when they reach infinity. And so it's not just an initial data problem at t equals minus infinity and evolve forward. I get to play with the theory by adjusting boundary conditions as we move in time here. And I think that's all that I wanted to say about ADS CFT. Are there any questions? So well, again, as Daniel said, this is not covering the entire geometry, as Paul knows. What it's doing is it's covering a patch. So it's like I write down Rindler coordinates for flat space. I only really cover a piece of the geometry. And so what this geometry, the way you can get it is you cut this by a null plane, well, one going up and one going down, and then you get something that the boundaries of that patch look something like this. So there's two planes that cut through my cylinder, and if I set t equals, these coordinates as a constant, and I go to r equals 0, I would actually end up at this point way over here. If I go to r equals 0 and let time go to infinity, I end up on this horizon, or this boundary, this upper boundary of the patch. If I go to t equals minus infinity, r equals 0, I would be probing that boundary. So it's very similar to a black hole horizon, or it's probably closer to a Rindler horizon. But the idea, you're looking very unhappy. But the basic idea here is that this is a nice coordinate system to work with and do our calculations. But with that, I'm not covering the entire space-time. I'm only covering things in a tiny, well, this cylinder goes on forever, so it's a tiny wedge in here. So this is a set of coordinates that it's adapted to if I want to study the conformal field theory in just flat space Minkowski coordinates. Oh.
So in this picture, r equals 0 is far away from the boundary, but as drawn on the board there, it looks like r equals 0 is on the boundary?
Yes, that's very paradoxical, isn't it? Yes. An astute observation, though. Are there questions? Oh, there's a question over here.
Is it generally believed that any CFT could be realized holographically, or is there a notion in which there are like boundaries?
You betcha. But they will. Oh, I erased it. Rats. Yeah. So being a card-carrying string theorist, well, I think I still have my card. I'm happy to say that any CFT has a holographic realization. The problem is that on the ADS side, I don't really know what to expect. I mean, what I told you actually, nope. What I told you earlier was that in our favorite example, what we had on this side was actually a string theory. And I told you, I confess that I don't actually know how to deal with that string theory in that space-time. And so we go to a special limit where all I'm doing is I'm studying Einstein gravity. And so the typical CFT is just, I mean, it's going to be something on the ADS side or on the quote-unquote gravity side, which is going to be unmanageable with our modern, well, with the techniques that we know about. So it's not going to be a theory that's close to the kinds of theories that I'm going to be talking about today. Other questions?
Are the gravitons supposed to actually be quantized, or is it just an Einstein gravity?
No, I mean, I can think that those are, there's a string theory that lives here. It's a quantum theory. It's supposed to be quantum gravity, and so you can think that quantizing the gravitons is an approximation to building that string theory.
But so the string side is quantized, and then you can get gravity in some way, but do you lose the quantization, or is there some way to go from the quantized gravitons to the other direction?
I'm not sure. What was the other direction? I mean, because I want the lecture to end roughly on time, I'll say, come ask me afterwards. I'm sorry. Unless there are other pressing questions, we will move ahead. And what will we move ahead with? Well, what we want to do now is we want to think about the holographic version of entanglement entropy. And so hollow entanglement entropy. So what we've been talking about in all the lectures I had in the first board, again, was we are thinking about a quantum field theory. Well, here's a quantum field theory. It's the holographic CFT. And we want to divide the space up into regions by introducing an entangling surface. So in this particular cartoon, that picture would live on the boundary of ADS space, and hence I'm drawing the entangling surface on the boundary. Just wanted to point out why I came up with that name. And so there's some calculation that one can imagine that we're going to integrate out conformal field theory degrees of freedom here, get a reduced density matrix, et cetera, et cetera, et cetera. But as hopefully we've learned in the past 3 lectures, those are hard calculations. And this is some strange conformal field theory with a large number of degrees of freedom and at strong coupling. It's not likely to be any simpler to try and work with that conformal field theory than any of the other examples that we may have touched on early in the course. But what we'd really like to do is we'd like to take advantage of the ADS CFT, and we'd like to translate that hard problem into a problem which we hope is simpler, but that has a geometric or a gravitational description. And so that's what the folks Shinsei Ryu and Tadashi Takeyanagi did some 6 years ago. So this is HTH/06030001. And so what was their proposal? Their proposal was, well, if I want to evaluate the entanglement entropy, what I'm supposed to do is I'm supposed to think about all surfaces that hang down into the bulk, which reach out to the boundary of my ADS space in a way that they just touch or connect with R equals infinity along this entangling surface. So there's some class of surfaces, that's sort of a boundary condition, but I can push this surface up and down. On each of those surfaces, I'm supposed to evaluate this formula, which is fairly familiar. So I'm evaluating the formula that we associate with black hole horizon, or the Bekenstein-Hawking entropy, on that surface. And then what I'm supposed to do is I'm supposed to extremize, or I'm supposed to vary the surface, and I'm supposed to find the minimum value of this quantity. Again, we're in surfaces which have a boundary on sigma. And the extremal value will then be or correspond to the entanglement entropy in the boundary theory. Well, there are many questions one might ask. The first one I will ask for you is, well, why should the extremal surface hang down into the bulk here like that? Certainly in my cartoon, it seems like the minimal area surface will be one that just stretches straight across. But this is, of course, this is the redshift in effect. This, remember, going horizontally up here at large radius is a long distance, whereas going across here at small radius is a shorter distance. And so it's the effect of the redshift, or this, the r squared that just got erased, that means that the extremal surface will actually find a path where it dips down first, then goes across, and then comes back up, like that. So what's the next question? Oh, well, there's a small problem with the calculation as I've described it. Here I've got a surface and it extends out to r equals infinity. If I try and integrate the area all the way out to infinity, of course the answer that I'm going to get is infinite. Well, I may have described that as a problem. It's actually a feature of the calculation, because one of the first... Oh, there's a question?
Wasn't entropy supposed to be valued on a specific time, at a constant time, here you're actually going?
Yeah, no, it was. So that was implicit when I drew this picture here. When I draw this picture in the field theory, I always say that the first thing I do is I fix myself to a constant time slice. And so I just ran out of dimensions in the picture, but there's some other direction in the boundary that is time.
So this is
And
the whatever time?
this picture would just be a time slice of the boundary theory. Of the,
Well, like smaller radius, so
this surface, well, okay, I can comment on that, or I was going to comment on it later, but in principle, this surface could vary up and down in time as well as moving up and down in radius. Is that what you're asking?
yeah, so it doesn't ruin the...
So yeah, okay, so that was on the next, okay, so infinity doesn't bother him, that's okay. So there, no, just let me, so what I said here, well, I used the word minimize, or I wrote something that represents minimize, but I said the word extremize. So one of the comments is that typically, in discussing calculations of entanglement entropy, I said that the first step in the calculation was to Wick rotate and go from Minkowski signature to Euclidean signature. In that case, just pushing myself out of the time slice that I started with is just going to increase the area. And so this is something, though, that implicitly, when I say minimize, I should think Euclidean. On the other hand, there are going to be situations, for example, if I want to study or measure the entanglement entropy at different places in some dynamical process, like the formation of a black hole, then I'd have to work in a Minkowski signature metric. And in that case, it seems that, because there's a minus dt squared, that pushing it up out of our favorite time slice, we're going to minimize, or we're going to reduce the area. And so this is really then, what I get to warn you is that when we're working in Minkowski signature, what we're really doing is we're extremizing. And so we're looking for saddle points. It's not the strict minimum of the area, but the surfaces that we're going to find are saddle points of the area as a functional with the boundary conditions that I specified. Yeah.
Can you say something about where does the extremum come from, and how is the strong between different extremum from?
I can, but I'm not going to skip ahead to, that's many pages ahead, and I'm probably not going to satisfy you anyway, but are there other questions? Is anybody bothered by the fact that it's infinity? It's a feature. Why is it a feature?
It's supposed to be infinite in the field theory.
There you go. Someone was paying. That makes me feel so good to know that somebody's been paying attention. As he said, it's a feature. One of the first things that we learned was that the entanglement entropy in a quantum field theory is going to be infinite unless we regulate. And so the fact that I didn't talk about a regulator here and I got an infinite answer should be no surprise. And so how do we regulate? Well, the problem was, just just to say one more thing about that infinity. Why was there an infinity? Because we went and we included all of the area out to infinity, out to very large radius. But that's the place where I said that we were probing the ultraviolet or the short wavelength degrees of freedom. And so this infinity is really a UV divergence or a short distance divergence. And so it really does match to the kind of divergence that we were talking about in the quantum field theories. To make sense of the calculation, we need to regulate. How do we regulate? Well, we don't integrate out to infinity. Rather, we introduce some cutoff surface. At some large radius. And that's actually a standard thing that we do in ADS-CFT calculations, and it turns out that that's the equivalent to introducing a short distance cutoff in the boundary theory, and the short distance cutoff is inversely proportional to that large radius. If I make the radius bigger, the cutoff distance in the CFT gets smaller. If I make the radius smaller, then the cutoff gets bigger. The units aren't quite working here because I've got a distance and a 1 over a distance, but there's a conversion constant, or there is a scale available in the problem, namely the curvature scale of the ADS, that capital L, and so the formula goes something like L squared over R naught. And then the claim I'm going to make is that, oh dear. Well, the claim is that when we regulate the problem like this, in fact, what we find is that the leading contribution is just nothing but an area law term, as we might have expected from our previous discussions. But this being a school, I wanted to see this in more detail. And so let's recall the metric that I wrote down. It was ds squared equals r squared over L squared minus dt squared plus dx squared plus L squared over R squared dr squared. And these were our CFT directions, and R is our holographic direction. So if we really want to calculate an area, the first thing we're going to do, well, this is just in the boundary, and it's, let's say t equals 0. We're going to have our favorite picture, but we're going to adapt the coordinates. I'm not going to use Cartesian coordinates, but I'm going to say that in a particular problem, we'll adapt the coordinates so there's a bunch of y's that run along the entangling surface, and then there's going to be some coordinate, which I'm calling sigma here, that goes orthogonal to that entangling surface. And for our purposes, we won't have to worry too much about how those coordinates really cover this region in here. But I can also look at this. So this is the A, the sigma, and my B. So I can look, here's the ADS boundary. I'm now going to draw a cross-section in the radial direction. So this is R now. This is my sigma. It's just, because I'm running out of dimensions, it's just that point here. This side I'll call A, this side I'll call B. So sigma run by, as I drew it there, points into the A region. There's also, so this is the boundary. I said that there's some cutoff here at large radius, and I'm going to choose that. Well, we chose it as according to that formula there. And there's going to be some extremal surface that bends down here into the bulk, and it's going to be specified by choosing some profile for the sigma. So I'm going to have sigma as a function of y, where I am on the entangling surface, and where I am in the bulk. Or that's one way to specify the problem. But the interesting thing is that because of that r squared over L squared, I mean, to move across costs a huge penalty when we're in the extreme or near the boundary here. And so the way that the surface deals with that, a universal feature is going to be that the surface, the first thing it does is it just falls straight down into the bulk before it tries to move across. And so what that means is then that up here, near the boundary, the sigma is I can just think of it as being 0. And I don't have to worry to identify this leading singularity or this leading contribution from the UV degrees of freedom. I don't really have to worry about any of the details of this extremal profile. But we can then, armed with that intuition, write down some formulas. Actually, well, I'm just going to rewrite that formula. Oh, okay.
No, I couldn't hear the question that was posed before, and I'm curious, what was the question? Why is this prescription the right prescription? That's what you're going to get to.
Yeah, I've got half an hour. Yeah, okay. I just wanted to well, I'm supposed to evaluate areas. I had another example, but I don't think we're going to get to it. But this is a very simple calculation. What we want to do is we're told to evaluate this Bekenstein-Hawking formula on the extremal surface. And so what does that really mean? Well, there's this coefficient that comes along for the ride, but we're going to be integrating over some set of coordinates which parameterize where I am on the surface. So the choice that I made over here is there's a bunch of coordinates yi that run around the entangling surface, and then the extra coordinate I'm going to use is the r. Note that the dimension there is d minus 1, and so it's the same dimension as the region in here. But it's not enough. We're doing geometry. It's not enough just to integrate over coordinates. We have to keep track of what's the metric induced on this particular surface. I'm not really going to have to worry about it too much in this particular case, but let's start writing out what that integral would look like. There's an integral over my y's. There's going to be some interesting stuff in going from Cartesian coordinates to the y's, and so I'll just write that as a square root of h sub y. There's going to be some interesting metric on this surface in those coordinates. But I've also got this factor of r squared over L squared. And so for each one of those y's in the, oh, I didn't say that. But this is the determinant of the induced metric, and then I'm square rooting it. So in that quantity there, after the square root, for each one of those y's, there's going to be a factor of r over L. And so there's an r over L to the d minus 2. The other thing that I was supposed to integrate over was the radius. And it comes not with an r over L, but rather an L over r, like that. And all I really care about is the upper end of this integral. I want to find out what the leading contribution out there is. And we had said that the maximum radius was, well, given by this, well, the inverse, we're going out to r naught, and so that's L squared over delta.
There's an r, shouldn't the r integral be?
Yes. But for the purposes of pedagogy, I want to say that these guys are associated with this part of the calculation. That guy is associated with that. But yes, I'm integrating over those. So what I'm doing is I'm evaluating, or I'm asking about an area, but it's an area in this geometry. And so I'm going to move around in the y directions, and there's going to be then some interesting stuff coming from this part of the metric. But each one of those contributions comes with an r squared over L squared. And then you take the square root, and it just becomes an r over L.
Why do we have to use this radius geometry? Because we can, by equivalence, we can calculate just conformal field.
Yes, you can, but the idea is that's a hard calculation, and this is an easier calculation. So we're going to calculate it in the geometric fashion. The nifty thing is that what is this? This is an integral over this boundary, and so that's going to give us the area. So that is the thing that before I was calling A sub sigma. That is the area of the entangling surface measured in the CFT metric. Then there's a bunch of L's running around, and it looks like I left those in the integral. So there's a dr, and then there's an r over L to the d minus 3. And again, I only care about the upper end of the integral. And you massage that a bit, and what you get is L to the d minus 1, 4 d minus 2, gn, and then there's an A sigma. And then there's a bunch of deltas that come out, but it's precisely delta to the d minus 2. Plus dot, 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 dot.
Is it obvious that that's the minimal surface?
Well, okay, you had to take my faith for it that the minimal surface, that the first thing it's going to do is it just falls, the leading approximation falls straight in. Given that, then I don't have to worry in detail about, if there was an interesting profile, there'd be an extra bit in this integral. But I don't have to worry about that if it's just falling straight in. And so, it just takes that, well, to just evaluate this part, I don't have to worry about the rest of the details. A comment which I'll put here is we had the area law, but there's also this term with the ADS curvature scale to some power over g Newton, and that's really I can think of that as the ADS scale over the Planck scale, and then there's a power d minus 1 here. And that's something that it turns out you can associate with a central charge. I'll put that in brackets, but the kind of, the central charge is the C, the A, the C, the things that were appearing in various calculations that were running. They're, in this particular theory, going to end up in this holographic description. Those central charges are proportional to this quantity here. But basically what that's doing is it's counting, or it gives you a count of the density of number of degrees, the degrees of freedom, or the number of degrees of freedom in the boundary theory. Oh, sorry.
Maybe I've missed that, but the coefficients of the CFT metric in the ADS metric, that is R square over L square. Is there some interpretation to that? Or does it just turn out to be right?
Is there an interpretation to it?
There's some reason for that. I think you just wrote down this metric and we accepted it, but
Oh, well, yeah, okay, so it's the right metric because it's the ADS metric if the curvature scale is L, so it's right in that sense. Remember, it's a, well, okay, I'm not sure if I'm going to explain anything. Remember, what we're talking about is a CFT. A special property of a CFT is I can scale the metric in any way that I want. In particular, I can do global rescalings. So when I talk about the CFT metric, I could talk about it being this metric, or I could talk about it being that metric times any coefficient. Well, here's a coefficient. And so it was just my choice or conventions that the way I identify that metric is I just threw that away. And I said, my convention is going to be that, you know, I look at the ADS metric and I pick this out, and that's going to be the CFT metric. So that's a choice, and you have to make certain choices at different steps in your calculation to be consistent with that. I could have made other choices. I could have, in fact, I could put an arbitrary, it didn't have to be an L. I could have put an arbitrary scale in there. It would have still been ADS with the curvature scale L. So there's a lot of freedom, and it's basically because we're studying the boundary theory is a CFT that we get away with it. Is that okay?
Mostly for convenience.
It's for yeah, it's a convention. It's a convenient convention.
Can I ask a question?
Sure.
So this minimal surface, it depends on where this geodesic ends, right? And then returns.
Yeah.
So, but in the integral, you didn't specify it, right? It's you specify the initial value as per.
Right. And that's because all I cared about was I wanted to show that what was coming out of this calculation, the leading order, was the area law. If I wanted to do a proper calculation, I wouldn't have just drawn an arbitrary curve here. I would have picked some interesting, simple entangling surface, and I would have worried about all of the details of the structure of the profile, and there would have been a full integral. It would have had a lower end and an upper end, and we would have calculated, we would have done a proper integral here. And as I said, there would have been more bits to, there'd be some extra complications behind the board there on what goes into defining the induced metric or the measure on this surface.
So then, can I say that there's no computation method to find this minimal surface for a given surface in the boundary?
No, there is, unfortunately.
Given boundary shape, I can find this.
In principle, yeah. Unfortunately, we're not going to talk about it today, but it's an exercise. Maybe I can photocopy those pages or something, and Patrick can post them. I just started to do the problem in the homework set to give you a flavor for how those calculations go. Where? Oh, way over there.
Probably not all close, but is there a role for the trace anomaly to play for this?
Yeah.
Like, is there, yes.
Yeah.
Is there a way to get the CFT on the boundary to somehow sit in some generic curve back?
Yes.
Okay. Are you going to tell us this story?
No.
I think you already knew the answer.
It's the optimism of youth. Ask me afterwards. I mean, there's an interesting story there, and it's an essential ingredient in sort of identifying those RG flows and what was flowing. It was essential to understand how the trace anomaly gets translated here and how you identify central charges and things like that. But we're not going to get there today.
In the answer, depending on L, so that L coming from the ADS side, not the conformance side.
Where's there? Oh yeah, there's an L in the answer. There's also an L Planck. So this is stuff that has to do with gravity, but it appears in a very special way. And what I was saying is you can take this quantity in the gravity, and somebody else has worked it out. I know how to translate that into a quantity in the CFT, which in many cases I can identify as a central charge in the conformal field theory. So it's part of the dictionary that says, I always have to be able to translate gravity answers into CFT answers, and so that's part of the dictionary.
If we calculate, if we were able to calculate based on conformal field theory, what's the quantity which is the same as L over L Planck?
So if I was doing a two-dimensional boundary theory, up to some if I was doing a two-dimensional boundary theory, this would just be L over L Planck, and up to some constant, that would be equal to the central charge C of the two-dimensional boundary theory. But let's, so just a couple more comments. One is, we can persist, we can think about, the corrections or higher order corrections. We can work with the profile, and we'll see that there's an expansion here in powers of, something related to the size of the region over delta. You can also, related to the question over there, you can also do this very carefully and expand near the boundary using something called the Pfefferman-Graham expansion. And you can actually identify then that each of those terms has a geometric origin. Here I have the area. Then what I would see is that there's a term here that involves an integral of curvatures over delta to the appropriate power. And then there'd be curvature squared, et cetera, et cetera. But that's all very much in the, advanced class that we're not going to get to today. A comment, though, is at this point, what I said is Ruan, Taki, and Agi proposed this, but their prescription was a conjecture. It was sort of a rabbit that they pulled out of the hat and said, here, let's calculate. What do you do with the conjecture? Well, either you're smart and you come up with a derivation, or you take the conjecture and you test it in various ways. And so what I wanted to do was just describe a few tests of the Ryu-Takanagi prescription. And basically, this is a story of string theorists learning more and more about entanglement entropy and how it should behave, and then seeing that their prescription gave you the right answer. So number one, the first test is, in my list anyway, is that I got the area law to come out. And so that's a rather generic feature. Number two is actually, we've alluded to before, but for a d equals 2 CFT, that's a situation where there's a lot more control, and there's some nice results by Calabrese and Cardi, which formula that we saw before, that the entanglement entropy for an interval, so if I have so I'm in d equals 2, a time slice, I'll make it a circle. The circumference of the circle I'll call C, and the region that I'm choosing I'll say has a length L. Then there's an expression with some interesting geometry, C over pi delta sine of pi L over C. And then there's a coefficient here, and that is another C, the little c, which is the central charge. And so what would be the holographic version of this calculation? Well, I would go to a three-dimensional ADS space. The extremal surfaces then are just lines in the bulk, so they're space-like geodesics. And so what you need to do is you need to study space-like geodesics that join, or find a space-like geodesic that joins the endpoints of your interval in the boundary. And what you find is that when you go through the calculation and you apply the appropriate holographic dictionary entry, that you nail this formula. You get all of this interesting geometry, and you get precisely the right prefactor here. Another interesting property, what did I do? Oh, there it is. Sorry?
Is it for any central charge or the limit of large central charge?
So what Calabrese and Cardi did is they did a calculation that applies for any CFT, and so any two-dimensional CFT should satisfy this formula. Here we're studying special holographic CFTs, and in fact they also, by that prescription, satisfy, or you get that result. There's also a similar result thinking about a thermal ensemble, there's cinches and betas appearing in the calculation, but you can also reproduce that from ADS3. Another simple property is in a pure state, I should find that that the entanglement entropy of some given region is equal to the entanglement entropy of the complement. I.e., if I integrated out the outside and I did the calculation and got SA, I could alternatively integrate out the inside and work with the reduced density matrix for the complement, and I should end up with the same entropy. And here, it's just proof by pictures. So this is now a time slice that I cut through my Penrose diagram of ADS space. So this is a cross-section of ADS space. So in principle, this is a d-dimensional geometry. My boundary is d-1 dimensional. But there's going to be some entangling surface here, which I'll just denote by those. And so the inside is A over there. The rest of the boundary makes A bar. In solving this particular problem, I'm going to find an extremal surface that matches up to sigma in the boundary. On the other hand, if I'm thinking about A bar, I'm supposed to find an extremal surface in the boundary, in the bulk, that matches up to that same sigma. And so I get exactly the same answer. And so in that particular case, well, from the holographic perspective, it's obvious that what I'm getting is that. And the same would apply if this wasn't just empty ADS space, if there were some gravity waves or some particles floating around in there that were deforming the geometry, I'd still end up reasoning in the same way. And just as a reminder, this is ADS boundary and the bulk. Blah, blah, blah. Yeah.
For the case where the CFT is 1 plus 1 dimensional, the ADS side is 2 plus 1 dimensional gravity, and there's formal equivalence to Simon's theory with some horrible gauge group SL2R plus R. Can you do a calculation from that perspective and the right answer to you? Does that?
Sure, yes, you can. What?
I don't know. Okay.
No, the answer is yes.
Is it difficult?
How difficult is any calculation? It's in the eye of the beholder. No, I don't think it's any more difficult than, well, okay, it would be more difficult for me. I like calculations like this, thinking about, but in fact, people have been studying that in the past year in not studying gravity, but higher spin versions of gravity in ADS3 and building the extensions of the Ryu-Takenagi. But there it's intrinsically sort of in this Chern-Simons gauge theory framework. Do I want that beautiful picture or no?
What happens, so, the question is nothing connecting to us, what happens when it's not a pure state?
That's an excellent question, and I was going to skip over it, but since you asked. So what's an example of something that's not a pure state? Okay, so an example that I told you about, let's compare to a thermal state. In that case, I draw the same picture, more or less. I'd have my cross-section of ADS. I'd have my sigma here. This is my A. This is my A bar. The difference now, though, is that there's a black hole down in the middle of the space. So there's something interesting happening in the geometry. And so it turns out then that, in this case, I'd find this surface for S of A, but that there's another surface that wraps around the opposite side of the black hole for S of A complement. Now, you could object to that because I'm actually invoking a new rule that I didn't tell you about. And the new rule is that, sorry? Almost, yeah. So the new rule in a fancier prescription or a fancier language is that the extremal surface should be homologous to the boundary region. And that basically means what you said. It means that I should be able to take this surface in the bulk and just push it up to the boundary here. In this case, I can take this surface and push it out here, but there's an obstruction to taking this surface and pushing it out the black hole. It gets hung up on the black hole. And so, well, okay. Since we're that far along, then what we find then here is that SA is not equal to SA bar. But then this was 3, so test number 3.5 is that there is another inequality that you can play with in this particular situation. And so what this inequality says is that the absolute value of SA minus SA bar should in general be less than or equal to the entropy of the union. And hopefully I got that right. Patrick's writing it down. He must agree. But in this case, what is the union? Well, the union is just the entire boundary. And so what I want is to find an extremal surface that is homologous to the entire boundary. I need to find a surface in here that's going to be now a closed surface that I can push out to the boundary, but I want it to be an extremal surface. So what's that going to do? Well, it's going to collapse down. If there was nothing in the middle, it would collapse to 0, and I'd see that I'm in a pure state. I get 0 entropy. But in this case, it collapses down, and it sits here on the horizon. And so what this turns out to be is just the black hole entropy, or A over 4G, A of the horizon. And so with a little bit more fidgeting, you can actually argue that this difference is always going to be less than the black hole area, or the entropy associated with the black hole horizon. So that's another, well, having gone this path, that's another test or semi-test. And I should attribute that to Veronica Hubney, Mukund Ragamani, and Eric Tunney. So can I go to 5 o'clock? I've learned that I have to set a large upper limit to So there's one other fun one that I wanted to show, and then, then I have to say one other thing, and then I have to show you some interesting pictures. So 4:15, here we go. So the other one, a fun one, is another proof by pictures is strong subadditivity. And this is Hedrick and Takiyanagi. So again, if I'm thinking that I've got two overlapping regions, I can write strong subadditivity as the entropy of the union, the entropy of the intersection is less than or equal to the individual entropies, the sum of the individual entropies. And I think I got the inequality right this time. Sure. It's late. So let me draw the two calculations that I would do. First, I've got the individual regions here. So I said I've got two overlapping regions. So I'll call this one A, and I'll call that one B. This is, again, the boundary of my ADS space. And so what would I do? I'd find some extremal surface for SA that goes like that, and I'd have some other extremal surface that goes like that for SB. And again, I'm just drawing it in this simple way because I lack the artistic talent to do a higher dimensional picture. But in principle, these are not, intervals, but they could be regions extended in the boundary or in a time slice on the boundary. But now let's look at what we have on the other side of the inequality. Well, we have the same pieces here of the entangling surface, but this one would now match up with this one, and so this would be the intersection, whereas this outer one would be, so that goes down there, this outer one would be the union. So in this case, what I would do is I would do something like that, and I'd do something like that. Now, the way that you show that there's inequality is you make the observation that what I can do here, these two surfaces are intersecting in the bulk, and so I can just tweak them so that rather than thinking that this line continues up, or surface continues up here, that it rather joins up to this one down here. And similarly, that this surface, rather than going through here, joins up to this piece here. Now, if I just think about this new geometry that I've invented here, that's a geometry that's in the same class as the surface here for the intersection. But I know that this intersection, and this surface is the extremal surface, and so this area is bigger than that area. Similarly, if I think about this new surface that I've constructed, that's in the same class as the ones that we extremized over to get this entanglement entropy for the union. Again, that's the extremal surface or the minimal area surface, so I know this area is bigger than that one. And so that's showing then just proof by pictures that this sum of holographic entropies is bigger than this set of holographic entropies. Implicitly, I'm thinking about a static situation there. You have to work harder in a dynamical situation where we had some interesting stuff happening. In that case, the surfaces don't necessarily intersect. But you can work harder and use some intuition from gravity or Einstein's equations. And Aaron Wall, in the past year, or a little over a year ago, wrote a paper describing how you would extend this kind of proof of strong subadditivity to a dynamical situation. Patrick, Matt Hedrick, and Alex Maloney also wrote a paper describing some other monogamy relations or inequalities. There's a bunch of other things, but I want to skip to the following, which is to say that those were all interesting tests of holographic entanglement entropy that were accrued over time. But one of the most interesting things that happened in the past year is a derivation by Lukowitz and Maldacena. And I'll give the Hep number and free myself from any obligation to describe what they did. Well, I'm not going to write anything on the board, but what they did is basically look carefully at, remember I described calculating entanglement entropies through the replica trick. And so one of the things they're doing is carefully translating the replica trick in the boundary CFT into calculations in the bulk gravity. They were also generalizing sort of Euclidean path integral techniques that people had developed to study black hole thermodynamics to thinking about certain geometries where there's a compact time, but there's not a symmetry, a continuous symmetry around that compact or Euclidean time direction. And in any event, what came out of the calculation is that if I'm calculating the entanglement entropy, the way to do it is, or what comes out at the end of the day, is evaluating the Bekenstein-Hawking formula on an extremal surface that matches up in the right way. But now the thing that I wanted to do last of all was show you some interesting pictures, and to show you those pictures I wanted to go to the computer. Are we? Yeah, well, look at that. Wow. So while that's happening, no. I hate to let you down. I'm sorry. Oh, come on. Oh, no. Oh, there it is. No, there it isn't. Okay. So what I wanted to talk about quickly was a connection between holography or ADS-CFT and MIRA, the multi-scale entanglement renormalization ansatz. Our friend Frank there was slagging or giving short shrift to this beautiful idea, but since Guifre is a colleague of mine, I have to tell you that no, this is an idea that's a beautiful idea and you should all go out and study it. I think there's interesting things to be done. But it's one of these matrix product states, but the matrices are put together in an interesting way, as Frank started to describe yesterday. Basically, I've got well, I'm describing a wave function on, say, a set of spins, a one-dimensional chain of spins up here. But there's an interesting set of matrices that are put together. As Guifre would describe it, there's two sets of matrices, one being called disentanglers. Their job, well, come back to that. There are the disentanglers, and then there are the isometries. So what the isometries do are they're removing or reducing the number of degrees of freedom. But what the disentanglers do is then remove short distance entanglement. So in this stage, I'm taking these two spins or these two sites and reducing it down to one. But those sites might be correlated with their neighbors. And so the idea is that these operations here, their job is to remove correlations with their neighbors. And we continue through the process and we go to a fewer and fewer number of sites at each layer. One of the interesting features, or the way that it was constructed, is in fact all of these matrices are unitary matrices. The way that you make this matrix a unitary is you think that there's a reference state in some, well, whatever our favorite state is here, that is being, if you're going in this way, this state is being mixed in, or if I'm going that way, I'm projecting onto a particular state. In producing the reduced lattice. Now, it was Brian Swingle's idea that there's actually a close connection between that construction and the ADS-CFT. One way to see it is this discussion about how lengths were reduced, being proper lengths were shrinking as I went down. Similarly, if I think about two sites here and their influence at different layers, as I move down through the lattice, you can see, maybe that wasn't a good choice. How about this one? You can see that they're moving closer and closer to each other and actually shrink down to a single site after a finite depth of the circuit. But another thing that he focused on was the idea of entanglement entropy. And so I wanted to show you some nice, well, okay, they may not be up to your standards, but there's some pictures. One reason I know they're not up to your standards is I'm going to take these blocks and just reduce them down to x's or x's with a dot. So an x with a dot, that dot is just the reference state. Here it's the unitary with two ends, so that's the disentangler. So here is then a representation of a ground state wave function. So there's some circuit here. UV is up, IR is down. Here are the disentanglers, and here are the isometries in blue. I want to calculate an entanglement entropy, so the thing I should do is I should pick some region and say that I'm going to trace out and form the density matrix. How do I trace out? Well, or how do I form that density matrix? What I do is I take the conjugate wave function, or the conjugate circuit, and then I trace out over the degrees or the bonds that are in the exterior region here. Now, the nice thing about the construction was these are unitary matrices. If I take the conjugate, that's the inverse matrix, and so they just annihilate with each other like that. And so they disappear, and the circuit simplifies. And in fact, that simplification carries on down here. If I then have a region with, say, k sites up here, then I can call that an effective length. And well, okay, I've said that there are 2 k sites, or k disentanglers up there at the UV end, but this construction basically only has to go down k layers to describe this density matrix.
You probably mean 2 to the k. Log k.
Oh, yes. No, you're right. The font got messed. That was a 2 to the k. Yeah, I did a cut and paste. Sorry. It was 2 to the... Okay. So there are 2 to the k sites that disappear down into 1 after k layers. If each one of those layers gives you... Well, actually, Giffre argues in one of his first papers that there's a certain amount of contribution to the entanglement entropy coming from each layer that's proportional to the central charge. And so then you can put those formulas together and you get an expression like that. One of Brian's observations was, well, this envelope of the circuit, the interesting part of the circuit, looks rather like a minimal surface. And so that was one of the things that he said in relating this to ADS-CFT. But what I'd like to do is a little bit better than that. I'd like to say, well, in general, if I want to calculate things with this density matrix, I need all of this information, say, to calculate a correlator. But if all I'm interested in is calculating the entanglement entropy, or say the Rayleigh entropies, then I can simplify the problem even more. In particular, these quantities, these entropy measures, are going to be invariant under unitary transformations. Well, there are all sorts of unitary matrices up there, so let's multiply by some unitary matrices and, say, get rid of all of those disentanglers. In fact, you can carry on and you can simplify the circuit so that it ends up looking like that. Basically, we scrape out all of the interesting, or all of the structure on the inside of our density matrix as well. We end up with a new density matrix, but that new density matrix is going to give us the same entanglement entropy and the same Rayleigh entropies. And so what that says is that all of the information about these quantities is actually hidden in this narrow band that runs through the circuit. And so this is the point where we can say that, in fact, so I had this big circuit that went into constructing the wave function and the density matrix, but when I calculated this quantity, all of the only structure in there that really mattered was a tiny narrow band that ran through the circuit. And so that, in fact, then looks much more like the minimal surfaces that you see in the Ryu Takiyanagi prescription. And so, well, that's just an interesting observation, but it's perhaps the starting point for more research. I really think this is an interesting idea that I encourage people to think about. And that then brings me to the end of the lecture and the end of the lecture series. For today's lecture, it's just to say that, in fact, holographic entanglement entropy then is part of a dialogue that's opened up between the string theorists and physicists in other areas of physics. And I want to emphasize in this case, I really think it is a dialogue. There's a potential to learn about issues in the boundary theory. You might be able to use entanglement entropy as a diagnostic for various properties or phases in the boundary theory, in the boundary CFT. you might be able to use it to gain further insights. I mean, it's something I alluded to, but it actually pointed the way towards these new C theorems, or the F theorem. But perhaps there are other properties that one might be able to infer by studying this in a holographic setting. And so I put John's favorite question there. Maybe there's something to be learned about RG flows when we don't have Lorentz invariance. But the interesting thing to me is that there's also the potential, this is a corner of ADS-CFT where I think we can learn about the gravity theory, or what's going on in the bulk. So some questions there is we might try and understand what some other measures of correlations are, for example, the negativity. We might be able to understand things about the emergence of space-time, for example, from Mira or from other ways of thinking about holographic entanglement entropy. There's also the emergence of gravitational dynamics. We might understand why there are no firewalls. And again, you get to put your own favorite question there. And so with that, I will close and finish my lectures.